Welcome everyone. My name is Peter Salemink. I'm going to tell you something about distribution system analysis using Power Grid model today. I hope you're all energized still. Yes. Yeah, that's good. It's almost lunchtime, so that's always tricky. But in 45 minutes you'll enjoy a lovely lunch, hopefully. A bit about me. I'm a development lead of the Power Grid model maintainers. Scientific software engineer at Alliander, a Dutch distribution system operator. And I'm also a guest lecturer at the Eindhoven University of Technology. Today, I will first give an introduction, a general introduction, then an introduction about Power Grid model. Then I want to mention some highlights since the last presentation that was given by my colleague Tony last year here at the LFE Summit. Give a short overview of the community that we have, and then I want to dive into distribution system analysis use cases, so 3 different cases within Alliander to show how Power Grid model is actually used in the real world. So first, a short introduction. Most of you are probably familiar with distribution system operators, but maybe not all of you, so a really short introduction. We are responsible for operating the distribution grids, mainly on the medium and low voltage part. And I mentioned here, distribution system operator is not an energy supplier, at least for the Netherlands that's the case. I've had some interesting talks with people from the United States, for instance, where there should be is, because they are usually the same company. So then Alliander, that's the company that I work for. We have roughly 1/3 of the Netherlands, both in electricity and gas. So like in 2022, we had the length of our electricity grid was almost 100,000 kilometers. So it's expanding every year. These are a bit old numbers. And then some pictures that maybe some of you are familiar with, not these particular ones because these are from Alliander, but this is happening everywhere around the world. These are already from last year. So what you can see here is the grid capacities that we have as a distribution system operator. And as you can see, for using electricity, it was not okay anymore, but there were still some possibilities in 2022. And in 2023, they were almost all gone because it's all red. And for feeding in electricity to the grid, it was already almost entirely red in 2022. So we have a lot of issues, and the grid is full, at least by the old standards. So we can do a couple of things to solve these issues. We can either go for new assets and expanding the grid, so thicker cables, larger transformers, etc., etc. But it takes time, and there are a limited amount of mechanics. And as you can see on the right side, is it really necessary? Because we don't use the grid 100% for 100% of the time. Because, this is a typical picture of a residential area where a large part of the grid is unoccupied for a large part of the day. And when everyone comes home, they plug in their EV, start cooking on electricity. And there we have a peak that might exceed the limit. But the problem isn't there the entire day. So then we have to look into smart solutions. Can we shift the peak to another moment? Or can we do something else instead of expanding the grid? And that's what I want to focus on today. Because this calls for fast and accurate grid calculations. And that's where Power Grid model comes into play. So why Power Grid model? We have a well-defined software API in Python and C. We have high performance. The actual calculation is implemented in C++. Which also allows for the native parallelization of your calculations. It's available cross-platform, so it's available on Windows, Linux, and Mac. And it scales really well. So for near radial systems, it scales linearly. Then, short introduction about Power Grid Model itself. Well, now you know why to use Power Grid Model, but well, why use it in the first place? What can you do with it? It has power system calculation functionalities for symmetric and asymmetric calculations, so you can do single-phase and three-phase calculations with Power Grid Model. And we have different calculation types that you can do. So we have power flow, state estimation, and short circuit calculations. So power flow, the what-if analysis. What if these are the loads in the grid? Then we perform an electrical calculation to see how the currents actually flow within the grid. State estimation. That's what if we add measurements to the grid that have a certain uncertainty? What is statistically the most probable state of the grid? And short circuit calculation. So what if a fault occurs in the grid? What will happen? And there are different types of calculations. So for power flow, we have four different algorithms. So we have Newton-Raphson, which is the commonly used algorithm to solve these kind of things. We have iterative current, which for radial networks is equivalent to the backward-forward method. That might be familiar to some of you. And then we have two approximation methods, linear current and linear impedance, which can be really useful because if you are doing calculations for the coming 40 years, then you don't need really accurate calculations, you need really fast calculations because the error in your data is way larger than the error that will be introduced by an approximation method. For state estimation, we have a Newton-Raphson method and iterative linear method. And for short circuit calculations, we have a method that's equivalent to the IEC standard, IEC 60909. And then some highlights since last year. So we did short circuit calculations. That's version 1.5 and above. So it's equivalent to the IEC standard. We introduced serialization in 1.6. So we have a way of loading and dumping your data to JSON and message pack datasets to easily store your Power Grid Model data. We have a Newton-Raphson state estimation algorithm that we introduced in 1.7, which allows people to do calculations in the real domain, which is particularly useful for distribution system operators, because you get to specify the standard deviation of both P and Q, so your active and reactive power separately. And for distribution system operators, we usually measure P if we measure something at all, and not Q. So it's really useful to be able to specify a different standard deviation there. And then the newest release is power flow with automatic tap changer. So you can do power flow calculations and find the corresponding tap settings to your voltage set points.
Peter, can I ask a question? How much of these features were developed from the maintainer as opposed to from the development community that's contributed?
All of these features were developed by the maintainers. And that's for Power Grid Model mainly the case. So the features are developed by the maintainers at this moment. But we do get a lot of feature requests also from other companies to implement these kind of things. Talking about the community. Well, there are Power Grid Model is used at many more different places than what's pictured on this slide. So what you see here is the three largest Dutch distribution system operators, Eindhoven and Delft University of Technology. There we also have close collaborations with. It's implemented in Panda Power and GridCall, and it's also integrated in the multi-energy semantic platform of RSE from Italy. And these are companies that we have close collaborations with. But, well, it's open source, so we don't know where it's used. that was the introduction part. And now I would like to dive into 3 different use cases of distribution system analysis. So the first one that I'm going to dive into is near real-time system operations. That's done within my department at Alliander, system operations. And then 2 different tools that are used for grid planning, one on the low voltage grid and one on the medium voltage grid. So first, system operations. The core functionality of system operations is active distribution system management. And we do that with a product that we call GAS. So it's a grid as a service. And it has capabilities of monitoring the distribution system, forecasting congestion, and activating flexibility. Because, well, if you gain insight and you have forecast, they also need to do something with that, of course, to make sure that there's some more grid capacity. So how does the system work? Well, we have an intake process, a build process, and a run process. Today I'll mainly focus on the run process, where we have a virtual grid consisting on measurements, equipment, topology, operational limits, customers and contracts and controls, so mainly all the data that we have. Then we want to create an integral overview. Well, we use the state estimation of Power Grid model for it, but we also use the short-term forecaster. For the people that were in the room half an hour ago, there's a nice workshop tomorrow by OpenStaff. So that's also used to create the integral overview. And then we dive into the problems and solutions with the dynamic security assessment and solution fulfillment manager. And then in the end, we apply solutions to either the grid, the market, for instance, through GoPacks or customer solution agents. And today I want to zoom in on a particular part. And that's mainly calling the state estimator, because, well, I'm talking here about Power Grid model. And that's the Power Grid analyzer. That's what we called it. So it can do 2 things. It has two of the functions from Power Grid model that it can use, state estimation and power flow. And for state estimation, the goal is to gain insight in the medium voltage grid in near real time. So we gain insights in the loading of the assets and the available remaining capacity. And for power flow, the goal is to forecast what will happen in the near future, so the coming 48 hours ahead. And the insights that are gained are how much flexibility do we need to activate and where. And then we can, for instance, do a call on GoPacks. Hey, we expect congestion tomorrow. Can you help us? So diving deeper into the Power Grid analyzer, we have data that's coming in. It's in the format of the Common Information Model, SIM. Probably many of you know it. It consists of topology, equipment, measurements, and steady-state hypothesis. So that's just 3 different data structures to define the entire grid. Then within the Power Grid analyzer, a SIM to Power Grid model conversion is done to create Power Grid model input data. Then Power Grid model itself is called to do a calculation, so either state estimation or power flow in this case. And then we get Power Grid model result. Then we do a conversion back, so from Power Grid model to SIM. And the SIM data is transferred again through our services and stored in our databases. But before we do that, we actually have to do something with the SIM data. There's a lot of information on this picture. I'm going to slowly walk you through it. So if we look at the original SIM data, so the node breaker model, then this would be the system of actually just 3 nodes. because we have well, it's not really clear, unfortunately. What's clearer on my laptop. We have a source, then we have a terminal, a connectivity node, terminal, switch, terminal, connectivity node, terminal, switch. So that's actually how the substation is well, what it looks like in the physical world. But that would increase your well, the complexity of your calculation tremendously, because you have a lot of nodes that don't really add value to your calculation. So what we do is we do a reduction of connectivity nodes to topology node, and then this entire system, so for instance an entire substation, is transferred into one topology node. And then this system can be represented like this, where we have a source, a terminal, topological node, another terminal, and then we get the cables. So AC line segment in SIM to the next node. So then we only have 3 nodes left, and those are the actual nodes that are useful for the calculation, because one is connected to the source, then we have a cable in between, this one has an energy consumer, the other one has an energy consumer as well, and then we can say something about the load that's used or generated by the energy consumers. So what does it look like in the real world? This is a real single feeder. So it starts at the left with the energy source, a node. Well, it has all the nodes, AC line segments connecting the different substations with each other. There's a power transformer and the energy consumer. So this is the low voltage grid. And well, there are 2 different types of colored dots. So the green ones are the actual measurements that we have. We don't have measurements on all places. And that's where OpenStaff comes in, for instance, where we have the purple dots. Those are forecasted or pseudo measurements. Well, what are the challenges that we're facing? Well, availability of measurements and other information as well. So first of all, I mentioned it before, usually we don't have reactive power measurements as a DSO. Tap positions might be unknown or registered wrongly, which results in really different voltages that are actually happening in the grid in your calculations, unknown sensor accuracies. Well, also the accuracy of the estimations and forecast. Well, on some places, if you have a lot of data to train your models, then it can be really accurate. But on some places, we are doing forecasting where there's no data available. So then the accuracy becomes less, and that might influence your calculations. And the impact of maintenance and fault situations on congestion management. So at this moment, it also happens that, well, if there's maintenance going on and things are switched, that doesn't always translate well to the data at this moment. So those are still some challenges that we're facing at the moment. And that was the real-time system operations. So now we get into grid planning, so more looking into the future, where I want to show you 2 different projects that we have within Alliander, the Delphi and HoloNet. So Delphi focuses on the low voltage planning and HoloNet on the medium voltage. And what they have in common is that they both heavily rely on power grid model batch calculations. So Delphi does a lot of time series calculations for various load profiles, and HoloNet does n and n-1 calculations on different scenarios that I'll explain in a bit. So first, Delphi. It's a digital product to support grid design by giving trustworthy insights in the loads and bottlenecks in the LV grid. So it tries to find the bottlenecks and possible solutions. Well, why is it necessary? Well, the expectations are that in the coming 5 years, the number of voltage complaints will increase by 10 to 25 times, not percent, but times in the low voltage grid. And in 2030, 50% of the low voltage grids will have bottlenecks, so congestion. This calls for future-proof investments, and well, to do a smart guess or educated guess for that, we have to do a lot of calculations. So the Delphi model takes in adoption models, grid data, connectivity, assumptions, power grid to do the power flow calculations and load profiles, and it delivers the bottlenecks. So as a short overview of what actually happens, so they have adoption modeling to determine the probability of adoption of different technologies by customers in a given year. They have customer modeling to generate multiple samples for the adoption of technologies to have a nice spread of your within your uncertainties. Load modeling, so to translate the current load profiles into suggested future profiles. Then power calculation, so perform a power flow calculation with power grid model to determine the distribution of the currents in the grid. And this all results in the expected bottlenecks and possible mitigation steps. And then, for now, I'd like to zoom in onto the power flow calculations that they do, because there are many. So for Alliander, we have 35,000 low voltage grids, where each low voltage grid typically exists of 100 to 1,000 connections. Then we want to do calculations on all of those grids for 3 different investment scenarios, where we use 50 samples of 15 random weeks with a 15-minute time interval. So, well, I'm not going to calculate it exactly, but for the ones on us that are good in math, it's millions and millions and millions of calculations that need to happen. So how do they do it? They use 2-layer parallelization. So first of all, they have multiple instances in AWS batch, where per instance they run one grid, one scenario. And then in one instance, they use power grid model batch calculations, where multiple threads per instance use the native parallelization that's available in power grid model. So there's a 2-layer parallelization to speed up the process. So far for Delphi. Now I'm going on to the next project, HoloNet. So it does 2 things, but it's on a medium voltage grid. It does 2 things. First, it creates an overview of the bottlenecks, and then it also generates different solutions for it. So different investment strategies that come out. Well, how do they do it? They have a grid representation by a Python model, which is called Alliander Python Grid. I'll tell you something about it in a bit. And it uses network it for graph logic, power grid model to do the power flow calculations, and it has a failure simulation engine to evaluate the robustness of the network, so doing n-1 calculations. So this is a typical overview of what it does. So they analyze the bottlenecks with calculations, and then they generate a lot of different new networks to solve these bottlenecks. So they add cable A, add cable B, reinforce cable C, add a new substation, etc. They try all these different things, and for all of them they do the n and n-1 calculations for different scenarios. So within Alliander we use typically 2 scenarios for these cases, a high load and a low load scenario, where a high load means all consumers use 100% of their load, and low load It's a scenario where all consumers use only 25% of their load, and all generation is generating for 100%. So then you get the two edge cases. Well, and then they try to find the solutions for it. So what does it look like in real life? Something like this. There are a lot of things changing. A lot of for each change that they do, a lot of calculations are done. So for every iteration, both the n and n-1 bottlenecks are calculated. And then they think of new solutions. So should we do a grid reconfiguration from one part of the grid to the other? Do we need to do reinforcements on a specific part of the grid? Or do we need to add new cables? And there is a nice teaser for you, because Alliander Python Grid is now Alliander internal, but we are working on open sourcing it and splitting it up into two different projects. One is Power Grid Model DS, so data science. So that's actually what Alliander Python Grid itself is. It's a Python wrapper around Power Grid Model that has more functionalities where you can easily add new components or remove components for your grid. And we have Power Grid Model Visualizer, which will be in an alpha phase. But it's a start, and we want to open source it, where we can also do visualizations of the grid. And then, seeing that it's almost lunchtime, I think I managed to stay well in time. I want to thank you all. My LinkedIn is over there, and I have the link to the Power Grid Model project below. I'm giving a project demo tomorrow as well. So if you want to get more information about how it actually works, how can you use it yourself, visit me tomorrow morning. I think it starts at 11. Then I can give you more in-depth information. And if you have any questions right now, I think there are still some minutes. So thank you. Within a couple of months. So a question in the back? Yeah?
Imagine that you are using SIM standard, and which version of CGMS are you using?
That's a good question. I'm not really sure. So within Alliander we use both SIM and CGMES. Well, and SIM is a common information model, but it's open to interpretation. So even within Alliander, we have two different models now that, well, they will converge together in the future. The SIM that I was talking about here is really just based on SIM and not CGMES. But there are teams also setting up and working with the CGMES standard. And then hopefully in the future, we can open source the conversions for that as well.
A couple of questions, actually. One is, when you start to think about distributed energy resources like solar or storage or other devices on the system, a lot of times they have volt-var controls and other interactions that might impact the power flow. Is that are those models captured within the Power Grid models as well?
No, they are not. So we have we just do the calculations, and if you want to do some specific load modeling, that's on the users of Power Grid model themselves.
And I guess the other question is, you talked about having some of the asymmetric load support for model systems. Does that go as far as some common and non-European settings where you have single phase medium voltage lines going for a while, or also capturing things like ground returns with also in Australia, they tend to have a single wire with the ground return. Some of those more non-traditional configurations.
Well, the single phase would be possible, but at this moment we don't have single phase loads yet. So we do have three-phase loads, so you can but then you need to specify them that they only eject into one of the three phases, for instance. So it's on our backlog to also implement dedicated single-phase loads, but that's not present yet.
So the idea of like single phase and then the line geometries and things like that to capture the differences in impedances, that's all eventually.
Can
Any other questions? If not, then I think we are perfectly in time for lunch. So thank you all, and